All right. Well, everybody, welcome to our next session. That was a great talk by Ellen. Thank you so much, Ellen. So our next session is Exoplanets and Unifying Space Sciences. A major goal of future exoplanet missions is the characterization of rocky planets in the habitable zones of their host stars. Given the vast complexities of our own planet, what can we learn from distant and data-limited observations of exoplanets with all spatial information compressed to a single pixel? This session will discuss the importance of cross-divisional interdisciplinary research to better understand exoplanets, including what we can learn from our knowledge of the Earth and the other planets of our solar system, and how planets interact with their stars. All of this will help inform the designs of future space missions aimed at characterizing Earth-like exoplanets. Our moderator for this panel is Giada Arney, research space scientist of the Planetary Laboratory at NASA's Goddard Space Flight Center. So Giada, with that, I turn it over to you.
Thank you, Jim. I'm excited to be here today. Exoplanets as an area of study is fairly unique in that it stands at the intersection of multiple disciplines and also multiple NASA divisions. So I'm really delighted to be here moderating a panel of interdisciplinary experts who all work on various aspects of these big questions. This panel today is going to be driven by question and answer. So I'm going to be asking our panelists questions, and then at the end, we're going to open the floor to any questions from the audience. So first, I'd like to briefly introduce each of our speakers in this session one by one, and then I'm going to give them time to give you all a brief overview on what they work on. So I'll start with Chris Reinhart. Dr. Reinhart is an associate professor in the School of Earth and Atmospheric Sciences at Georgia Tech. He works on the chemical and climate evolution of Earth's oceans and atmosphere through geological time, and he has applied that to considerations of the detectability of biosignatures, or remotely observable signs of life over Earth history. So Chris, would you give us a brief overview now of your research interests?
Sure. Thanks, Giada. Hello, everyone out there. Very glad to be here. So yeah, my interests and the sort of interests of my group are really sort of focused on the Earth as an integrated system. That's kind of the through line that runs through most of what we do. And so we're very interested in how all of the various sort of spheres and components of the Earth system interact to produce some of the large-scale features that we think of as characteristic of the Earth. So large-scale features of ocean chemistry, atmospheric chemistry, including things that might be potentially remotely detectable. And so the way that we kind of go at that set of issues is a kind of a mixture of observational sort of isotope tracer techniques and paleoceanographic techniques and theoretical modeling. And we sort of span spaces of very deep into Earth's past, so periods of Earth's history, billions of years ago, during which the kind of large-scale features of the Earth system were really dramatically different than they are today. In many ways, the earliest Earth is kind of an alien planet. And so a lot of what we do is just trying to reconstruct the sort of first-order features of ocean and atmospheric chemistry during those periods, and then try and get those reconstructions to sort of harmonize with theoretical models that allow us to say something about the kind of mechanistic drivers of those features that we're observing in the rock record. And so one of the things that kind of causes us to be very interested in is what are sort of the major planetary factors that structure atmospheric chemistry, which is kind of our window into the exoplanet community. So one of the things that we're very interested in understanding is how things like the abundance of oxygen in Earth's atmosphere and the abundance of methane in Earth's atmosphere have evolved over time, and what are the kind of planetary and biospheric boundary conditions that have structured the sort of topology of those evolutionary trajectories. And so we're quite interested in sort of using the Earth as a test case for our understanding of the planetary factors that control important atmospheric constituents that might be useful for characterizing exoplanets. Yeah, so that's kind of it.
Great, thanks, Chris. Well, Earth is certainly important because it is the planet we will always have the most data from, always, no matter what.
Indeed.
As next, I'd like to introduce Eddie Schweiterman. Dr. Schweiterman is an assistant professor of astrobiology in the Department of Earth and Planetary Sciences at UC Riverside. His research involves consideration of modern and past Earth as an exoplanet, climate photochemical and spectral modeling of planetary atmospheres, and consideration of the detectability of biosignatures on exoplanets. So Eddie, could you tell us more about what you work on?
Yeah, thank you so much for that kind introduction, John, and it's great to be here. Yeah, I use a combination of empirical and theoretical approaches to study planetary habitability and potential exoplanet biosignatures. And in particular, I use a suite of models, climate, photochemical, and spectral models, to simulate planetary atmospheres and surfaces and their potential remote signatures. I'm particularly interested in a few things. One is validating these models with observations of the Earth, as Giada mentioned, and other solar system planets. Improving these models by improving their inputs, because their outputs are only as good as their inputs, such as cross sections, things like that. And kind of vetting biosignatures, potential biosignatures and observables by changing so many of the dials that we have. You can change the. We have the sun around us, and it has a certain spectral energy distribution, and that impacts our atmosphere in certain ways. And then if you change that, you then change the chemistry that's happening in that atmosphere, and you also potentially change both the climate and you change the potential remote signatures that you get. And so when you're thinking about what trace gases in that atmosphere would be indicative of life, if there indeed was life on that planet, all of those things can change when you change those planetary parameters. And so can we be confident of that? And we can get into this probably in the panel later, but there's potentially abiotic processes that would mimic signatures that we'd otherwise attribute to biosignatures. And I'm very interested in breaking out what those processes could be and how we would determine that those processes are happening or not happening on an exoplanet, to give confidence in a true negative detection of a true absence of biosignatures or a true presence of biosignatures. And the reason why this is so important is that next generation telescopes and even instruments on the ground take a lot of time to develop. And so we want to make sure that we have the best possible chance of actually fully vetting the data that we get, and to be able to predict and anticipate perhaps where we could err is something that could potentially save us a lot of time, effort, and money in the future. And as Chris mentioned, the Earth as an exoplanet is so important, not just the Earth as it exists today, but through time. And so I'm also interested in looking at the spectral observables of Earth as it's evolved over geologic time, and it's changed so drastically in its atmospheric composition, and therefore the potential observables we could get. And that's just one, kind of through line in the whole huge parameter space we could have for exoplanets. But it gives us more than we otherwise would have. So that's a summary. Thank you.
Great, thanks, Eddie. I agree. The search for life beyond the solar system is such an exciting topic, but it's going to be one of the most difficult things we do, so we need to prepare for it. The next panelist that I want to introduce is Kathleen Mt. Dr. Mandt is the Chief Scientist for Exoplanets at the Johns Hopkins University Applied Physics Laboratory's Space Exploration Sector. Currently, she's serving as project scientist for the Isle Volcano Observer Phase A concept study in the NASA Discovery Program. And her scientific interests are very broad, ranging from planetary atmospheres to surfaces and across a wide range of solar system bodies, including comets, Io, Europa, Mars, the Moon, and more. So Kathy, given your diverse suite of interests of solar system bodies, could you tell us more about the topics that you work on?
Yes, thank you for the introduction. I am a planetary scientist, so I work primarily in our solar system, and I work on a lot of areas, but my favorite area is looking at atmospheres and studying how they have evolved over time using data from spacecraft. So I've used data from the Cassini mission and from the New Horizons mission in particular to look at the evolution of the atmospheres of Titan, Pluto, and then some Voyager observations of Triton to look at how that has evolved over time. And I think that this topic, as the previous speakers touched on, is extremely important for exoplanet science, because whenever we are observing an atmosphere of an exoplanet, we're really only seeing a snapshot in time for the entire history of that planet. And having an understanding of how atmospheres evolve with or without life is going to be very important for us to understand the habitability of exospheres. And our own solar system is the most important place to make these observations. Something else that I've gotten involved in is more policy and mission design work, particularly in the area of exoplanets and cross-division studies. As Giada mentioned, I'm the chief scientist for exoplanets at APL. And with that role has come the task of initiating an exoplanet program by leveraging our planetary science and heliophysics expertise. So our background as an organization has been primarily focused on doing planetary missions and heliophysics missions. But as a grassroots effort, we got together and started to realize that exoplanets was reaching a turning point where the focus is not just going to be on discovering new planets, but really digging in and characterizing and understanding them. So this is an important time where planetary scientists and heliophysicists can make important and valuable contributions to this growing field. So what I've been able to do is get involved in some work on mission design, mission implementation, and then working through assessment groups. I'm a member of the OPEG, Outer Planets Assessment Group Steering Committee, and I'm also involved in ExoPEG, the Exoplanet Program Assessment Group, SIG3, which is an exoplanet solar system synergy effort. And what we've done is we've gotten a group of planetary scientists and exoplanet scientists together looking for ways that we can create more synergy in the community. We've created some tutorial talks that are done monthly and they're recorded, so you can access them on the SIG3 website, so you can watch them later if you aren't able to make it. And we're also looking at ways to help the communities communicate better, because in some ways the exoplanet astrophysics side of things, they speak one language and planetary scientists speak another language. I'm also very interested in ways that we can leverage missions to advance exoplanet science, and not just astrophysics missions, but actual missions in the solar system. I've had the opportunity to serve as the deputy project scientist for the Interstellar Probe Mission Concept Study, which is a study that will go into the decadal survey as feeding in information for the heliophysics decadal survey. But one of our tasks from NASA with this mission design was to look at cross-division science that we could do in addition to the heliophysics science. Now, this mission concept would focus on getting out of the solar system as fast as possible. So we've been doing a lot of studies at how fast we can get out of the solar system with currently available technology, not anything that requires years of development. If we were to launch now, how fast could we go? And we want to study the heliosphere as a habitable astrosphere. But we also want to take advantage of a mission going so far out to look back at our own planets and look at them as we would see them if they were exoplanets. So we've been looking at observations and working with exoplanet scientists to integrate those types of observations into the mission concept before it even goes to the decadal survey. And we've also been working on other missions as well. With IVO, we looked at an opportunity to have exoplanet-like observations of Jupiter as a science enhancement option. If that mission is selected and the option is selected, we may be able to do that. So that kind of summarizes the work that I've been doing. I've been doing science, but I've also been looking at policy and mission design ways to get the communities together and enhance what we can do for exoplanets using all of the resources available at NASA.
Wonderful. Thanks so much, Kathy. You definitely wear a lot of hats. And for those of you in the audience, those tutorial talks that Kathy mentioned are very, very useful and wonderful resource for folks who are interested in getting into the space of exoplanet solar system synergies. So I highly recommend looking those up. The last panelist that I'm going to introduce to all of you is Allison Nort. Dr. Nort is the Astrophysics Instruments Senior Manager at Lockheed Martin. She's served as the NIRCam Project Manager for JWST, and she's been involved with the LUVOIR and HABEX Astrophysics Future Flagship Concepts, currently being considered by the 2020 Astrophysics Decadal Survey. She's also been involved with in-space assembled telescope studies. So Allison, could you please give us a little more detail on your areas of work and interest?
Yes, thank you, Giada, and thanks for the introduction and for the opportunity to participate on this panel. So I represent the engineering community that's developing the technologies to enable the direct detection of Earth-like exoplanets. The goal is ambitious, but realistically achievable with the robust investment needed for the technologies. So I'd like to provide a rather simplistic example to illustrate the challenge of direct detection of an exo-Earth around a sun-like star. So imagine you're in San Francisco and you're trying to take a picture of a firefly at Mile High Stadium in Denver. So the firefly is next to a light that is as bright as 1,000 stadium floodlights, but the firefly and the floodlight are separated by less than a millimeter. Of course, we're ignoring air and the curvature of the Earth, but hopefully you kind of get the picture. So to do this, we need a very large lens to collect that faint light of the firefly, while you simultaneously block out the floodlight by some method, much like an outfielder might block the sun as they try and catch a fly ball. So you'll need a long exposure time, and your setup had better be extremely stable, as any motion will cause the bright light to dodge the obstruction and fall on your detector, flooding out the firefly. So I know it's a very coarse analogy, but this example can be used to illustrate some of the technologies that are needed to be developed and matured to flight readiness. So for this example, and for direct exo-Earth imaging, we'll need a very large aperture. So as you know, 2 of the 4 flagship missions proposed for Astro 2020 have a primary goal of exoplanet detection. So HabEx is a 4-meter aperture, monolithic, and LUVOIR has options for an 8-meter or a 15-meter segmented primary mirror. So these are just example concepts, but it shows that advancement of these large apertures requires some development, although different types of development for a monolith or a segmented aperture. But it's not the greatest challenge in this mission, as a lot of that aperture size can leverage the developments on JWST. Next is starlight suppression. So the contrast ratio between the firefly, or our planet, and the floodlight, the host star, is about 1 × 10⁻11th. So the method of blocking out that starlight could be an internal coronagraph, an external starshade, or both. And development of advancement of both coronagraphs and starshades will need to continue to achieve that level of contrast. The Roman Space Telescope's coronagraph instrument is a technology demo, but it's going to go a long way to the advancement of that coronagraph technology. These missions will also cover a broad spectrum from UV to IR and require more advancement in coatings and detectors. And then we get to stability. So the stability of the system will require precise alignment, pointing, thermal control, while isolating the system from all disturbances in order to achieve stability of the wavefront error on the order of 10 picometers over very long durations. And the performance of the system will need to be well understood to predict performance and inform the error budgets. And this drives the need for very detailed and accurate integrated modeling of an entire observatory. So in preparation for the Astro 2020 Decadal Survey, all 4 flagship mission concepts developed and studied in detail. And part of these studies, each team developed a comprehensive list of technology development needs. For exoplanet detection, the broad range of categories of the technologies included things like coronagraphs, starshades, detectors, coatings, metrology, ultra-stable telescope systems, and integrated modeling and performance prediction. And right now, there's currently several technology development studies underway at NASA, at universities, at FFRDCs, and in industry. So these development efforts are essential to achieve the technology maturity that we're going to need to execute a mission like HabEx or LUVOIR, and to achieve direct imaging of an exo-Earth. But the goal is achievable, and the study teams concluded that it is possible to achieve that required technology maturity in all of these areas in the next 5 years with appropriate funding of these efforts. So that's kind of the background and a little bit about my own work. I'm at Lockheed Martin, and I'm leading a study team working on the challenge of developing the extremely stable large observatories through 3 parallel activities. So we're maturing technology first on non-contact vibration isolation and precision pointing. And through that, we're building a subscale CubeSat demonstration for that technology. Second, we're advancing picometer level metrology through two parallel efforts measuring optical path difference of light. So one method measures the phase difference and the other method measures the frequency difference, and they can be used to measure against each other. Finally, we're developing integrated structural, control, and optical models, which provide a predicted wavefront at the entrance to a coronagraph. So our integrated model is one part of a large modeling effort, which incorporates work from many others. So Ball Aerospace is leading a parallel team working on wavefront sensing and control modeling, and JPL is leading a team developing predictions for coronagraph contrast performance. So all of these integrating models are needed to predict coronagraph contrast of an integrated observatory. So I've highlighted just a few of the projects, but there are a whole lot of parallel studies underway to address that broad spectrum of technology development that's needed. And we'll have to apply all of these technologies and study results to mission that will directly actually image an exo-Earth.
Great, thank you so much, Allison. Obviously, we need to think about the technologies that we will require to observe these kinds of planets that we want to get at, not just the theory behind what we want to observe, but how do we observe? So on that note, I have a question that I want to address all of the panelists, which is about JWST, which is launching this fall. There's a lot of excitement in the community about what this observatory will be capable of across a huge range of space sciences, including exoplanets. So question for our panelists is, what excites you the most about James Webb? And also, what are you looking forward to beyond James Webb? I know a couple of you, including Allison, have touched on that topic, but you know, what's great about James Webb, and then what's great about what might be coming next? So if you could all tackle that question, whatever order you want, maybe the order you originally were introduced in might be easiest.
Sure. Well, the other panelists, I think, have much more interesting things to say about this one. I'm not so much of an observer, but I will say that, you know, one of the things that I'm very excited about is just some of the basic observational planetary science on the kinds of targets that JWST is going to look at. These close-in tidally locked planets around stars that are very different than our own star, and so some of the very basic kind of, you know, do these tend to have atmospheres, and how thick are they, for instance? Some of the sort of like very first order questions I'm really excited to see. But yeah, I'd actually be much more interested in what the other folks in the panel think about this one in particular.
Yeah, there's so much to say about JWST, but I think the thing that I'm most excited about is the idea that we could detect molecular absorption in a high molecular weight atmosphere. You know, and it seems like maybe CO2 would be the molecule to detect. And for example, of the 3 terrestrial planets in our own solar system with substantial atmospheres, they all have CO2. 2 of them are completely dominated by CO2. And one of them, Earth, of course, has CO2 is a trace gas, but it's very spectrally active. And so in certain wavelength range in the observing mode that JWST would be operating in, it is actually the most observable gas. And so we really have a chance to, for the first time, see these molecules in high molecular weight, that is not hydrogen and helium dominated atmospheres, and potentially detect both an atmosphere and start to figure out the chemical makeup of those atmospheres.
I would agree that the opportunity to see specific molecules in atmospheres of exoplanets is going to be an extremely important thing. And I have to admit my own bias to Titan-like worlds and the potential for detecting methane and ethane in an exoplanet that may not be as close to its star as climate-wise as Venus and Earth. So I'm interested in outer planets that could potentially be habitable. You never know with Titan. We haven't discovered life there, but it's a place of great interest for astrobiology. So I think for me, that's the most exciting thing, is looking for methane and ethane and other organic molecules in atmospheres.
Well, James Webb is my first child was the NIRCam instrument, because that was conceived long before my first child, who's about to actually go to college. So, and I've been working on NIRCam for the better part of my career. So I guess the thing I'm looking forward to most is seeing the first NIRCam images come back as the engineer. So what's interesting about the perspective is hearing the scientists and how you guys are going to use the instrument that we started building 20 years ago. So it's going to be really exciting to see James Webb working.
Yeah, it'll be fantastic to finally have that telescope in space collecting data. I cannot wait for James Webb's first light. But what's next beyond James Webb? A few of you have touched on this topic. Just sort of, thinking to the farther future of exoplanet science. Can you talk about or speculate about some of the big questions or some of the needs of the astrophysics community to answer questions that maybe won't be answered with James Webb?
I can give a quick answer, which is that James Webb is going to be an amazing first step for characterizing exoplanet observers, particularly those ones that cannot be characterized by Spitzer or Hubble predecessor observatories. But it does have limitations, and for example, we're not imaging the planet. We're limited in the wavelengths in terms of visible and UV wavelengths we can't see, and also sensitivity. And so, for example, it's very unlikely we'll see oxygen, even if it's present in an atmosphere with the James Webb Space Telescope. And so these future observatories, potentially a HabEx or a LUVOIR, would be able to see those other molecules, which have some really great, relevance to both habitability and biosignatures detecting life. And so I think we can certainly look forward to that true Earth analog with those future observatories, as Allison mentioned.
I would agree with Eddie. I think he's right on the point, and I think the one of the things that is a concern long term is ultraviolet observations. This is something very difficult to impossible to do from the ground, and once we lose the ability to use the Hubble Space Telescope, we lose UV in space. And I think for the future, ultraviolet observations and ultraviolet capabilities from space are going to be extremely important for exoplanets, for planetary science, and for other observations.
I guess my perspective on James Webb is that it's really interesting to highlight James Webb for me in an exoplanet talk, because when we were building NIRCam, exoplanets was never the goal of JWST. It wasn't conceived with any of those, and we put a LEO stop and a occulting mask as a goal. It wasn't even a requirement to be on the NIRCam instrument. So it's really interesting to see it being used in that way now. But it wasn't meant to be an exoplanet observatory, and now to see it that way is interesting. But yeah, there's a whole lot of more, as I mentioned, with the Roman Space Telescope, that is going to be a great opportunity, even though it's a tech demo, to do coronography for exoplanet imaging. And like Kathy said, the UV aspects, I think that there's opportunity there, right, for the picking in intermediate, smaller scale missions in the UV, in the Explorer class kind of missions that we need to work on to get them up there quicker to fill that hole after Hubble, before we can get a LUVOIR type of mission up there.
Yeah, and I guess I would briefly sort of echo all of that, and what Eddie was sort of alluding to in terms of sort of progressively moving closer and closer to Earth twin type systems. As an Earth scientist, of course, that's very exciting for me, and someone who thinks a lot about things like ozone and UV and different oxygen signatures that one could look at. But I also think one of the things that, from a sort of climate modeling and atmospheric chemistry modeling perspective, that James Webb I think is really powerful for is, in some ways it's forcing planetary scientists to think outside of kind of Earth-centric boxes, because in some respects there's just these are going to be the sort of new exciting observations that we'll have, and so we need to understand how these many of these targets are working, even though in many respects they're wildly different from the Earth, or from sort of Earth analogs. And so that's driving a whole lot of, I think, really interesting kind of fundamental theoretical research that I suspect is going to redound very strongly to the benefit of our understanding of observations as we get closer and closer to Earth, more Earth-like planets, because there's such a huge spectrum of behaviors even in that space, that the sort of widest reach of tools that we have is going to be really really useful. So I think that's another sort of powerful thing that JWST, the excitement around it, and the potential target types is really going to is driving a lot of real important steps forward in the theoretical realm.
Yeah, wonderful. And certainly for me, when I think about James Webb and the fact that it will be observing planets around stars that are much lower mass than the sun. So it'll be really, really interesting to compare how those kinds of stars are different and similar to the planets of our solar system. My next question for all of the panelists is, you're all involved in various types of work, and the scientists on this panel are all interdisciplinary researchers. So I want to ask you, why is interdisciplinary research so important to exoplanet studies in particular? And could you talk about that, but also about what do you perceive as some of the biggest barriers for conducting successful interdisciplinary research or developing interdisciplinary exoplanet missions, and how can we overcome those barriers?
So I can start this time. I think that planetary science in general has been inherently interdisciplinary. You need to have people with expertise in geology, people with expertise in physics, and expertise in heliophysics in various areas to really understand a planetary system. And exoplanets falls into that category as well, because we are studying planets that it's even more difficult to get data from. So you really need an interdisciplinary approach and perspective in studying exoplanets. I think one of the biggest barriers is, even though in planetary science we have a lot of experience with getting interdisciplinary scientists to work together to solve some problems, with the divisions at NASA, there has been this natural stovepiping between astrophysics, heliophysics, and planetary science, and even earth science, where the funding goes in one direction and it's focused on exploring science goals that are relevant to those divisions. And those funding pipelines end up standing in the way of getting people to work together. But I am seeing progress on the side of NASA. They are definitely making efforts to bridge these gaps, and the community is advocating for efforts as well. So I think we're at a turning point, and exoplanets is really one of the driving forces in this turning point, because there is this need to work across the divisional boundaries at NASA.
Yeah, I guess I could hop in on there. Yeah, I definitely would echo all of that. I mean, I think planets are complicated, integrated systems, and they are also embedded in a broader context that is itself a complicated system. The star-planet system, the entire sort of planetary system as it evolves over time. So just understanding an individual a planet from soup to nuts is hard enough. When you're walking across it and dropping instruments into its crust and putting submersibles on the bottom of its ocean, but when you think about trying to use sort of fragmentary, sort of top-down observations to say something about the sort of broader features of the entire system, in my view, the premium on having people from across disciplines becomes that much more important. And I think in terms of the challenges, I think Kathleen put this really well in some of her introductory remarks. I mean, one of the things I think here is language, and is getting people to talk to each other, and I think that's always kind of a challenge, and it's sometimes sort of characterized, I think, kind of unfairly as sort of jargony and pedantic sort of things, but I think it's just a very deeply human thing to get excited about something that you know a lot about. And when you're talking with people who are in the same space, you can use it as shorthand, and it can be more effective, and kind of shaking ourselves out of that to try and bring everyone along, I think is it. I mean, I find it to be a challenge, and something that I try to learn to do better over time, and something that I think as a community, it's really important to work on.
And I'll add something here on interdisciplinary research, although it's not really on the science side, but in the development of these missions, it's becoming increasingly critical that we have interdisciplinary research across engineering disciplines and the bridge between the scientists and the engineers. So, in the integrated modeling work that we're doing right now, we can't stovepipe one analysis and then throw it over the wall to somebody else and just say, okay, we're done, now you take it. There need to be these kind of feedback loops in design, analysis, and integrated modeling. We're working with the teams on the segmented chronograph development analysis team that JPL is leading. And so you have the scientists at the end of that light train going, well, what do I do with this coronagraph, and how do I, detect, if I get these wavefront error coming into my instrument, and how do I actually see planets in that, in our predictions, as I think it was Eddie that was saying, we need to predict what we're going to be able to see. And that has to go all the way through our whole engineering system to see, how are the thermal and the wavefront sensing and all of these different aspects interrelated. And we need to do it not just across an individual team of our engineers, of controls and thermal engineers, but across organizations, from the universities and NASA to industry teams, actually really integrated and working together, so everybody's bringing their best to the table, because it's a hard problem and we need a lot of different aspects of it.
Yeah, all those points were great, and I just add that we can't succeed unless we are interdisciplinary, and we can't succeed in this. If you look at the history of science, there was this transition from like the middle of the last century, everyone was a generalist, to now everyone is a specialist. And there are like very few generalists left. And I feel like what we need is more generalism, but with humility. So people aren't, claiming that because they dip their foot in multiple fields that they know everything, but that they can become the facilitators to glue together or bridge together all of these different facets, because everyone is necessary, and we can't succeed unless that whole chain is unbroken.
Wonderful. Yeah, those are all really great perspectives. And Allison, I don't think I've fully appreciated until now how how similar systems engineering is to system sciences, that we need to understand exoplanets. So I love that. So I have a question that maybe Kathy can start with, and then we can also throw it out to the rest of the panelists, which is about the solar system. And given the challenges inherent to exoplanet observations, as we've been touching on, many people have been looking to the solar system to help us understand those exoplanets, since we can understand the world of the solar system in so much more detail. So Kathy, could you tell us a little bit more about why understanding the solar system and these very nearby worlds can be important for helping us to understand exoplanets?
Sure. I think the biggest thing is that we can get data in situ in the solar system, in particular in atmospheres. Like the Cassini mission flew through the atmosphere of Titan, taking in situ measurements almost 200 times. And those in situ measurements, we barely scratched the surface at really understanding what we have observed with those measurements. So taking advantage of this direct access to atmospheres, which is going to be the most accessible thing to observe in exoplanets, is something that we really need to do, and keeping in mind that it's not just for understanding our own solar system, but that there is application way beyond. So looking ahead, this means that we need to start thinking about what observations that we can make in our own solar system in the future. We have this wonderful Cassini data set. We can start digging in and looking at Titan, but what atmospheres are we missing information on? And there are two categories of atmospheres in our solar system that I think are particularly important for exoplanets. That's Venus, which has been explored, but not enough for us to fully understand all the questions that exist with Venus's atmosphere. And then there are the ice giants, Uranus and Neptune. These are a class of planet that is very prevalent in exoplanet detections, but we have not had a spacecraft to actually orbit and explore either of these planets. This is the least explored class of planet in our solar system. So we don't understand how they formed. We don't understand the composition of the atmosphere. We don't understand their thermal evolution, which is important for observations of young planets. So exploring these somewhat neglected categories of planets and atmospheres, I think is going to be very important for the future of exoplanets and interpreting the observations that we're going to have.
That's great. Would anybody also like to comment on that question?
I could comment from the naive engineer point of view, but it seems that we've got a opportunity with our own solar system to actually bring back samples. You've got, OSIRIS-REx and Mars sample return, where not only are we making remote observations and in situ measurements, but we can actually bring back material to give us samples of the different kinds of materials and the building blocks of a solar system that might come from something like OSIRIS-REx. So I think that's pretty exciting.
Eddie, I saw you unmute, and then Chris unmuted.
Eddie, go ahead, please.
Yeah, I just add the technical point to these great points by Kathleen and Allison that, when we're observing an exoplanet, we're actually limited by being stuck in the solar system and the geometries in which we can look at a planet. So but even from a simply remote sensing standpoint, even neglecting all the tremendous information we get from in situ measurements, we can see the planets of the solar system from every viewing geometry. If we have the right platform, it's achievable. And this is really critical for validating our models of planets and our ability to predict and then interpret observations of exoplanets. And so that's a huge lever on exoplanet characterization.
And I would just, that's also a really good point. Just to sort of briefly echo and what both Allison and Kathy said, and tie it to something Kathy said earlier, being able to make in situ observations, certainly on the Earth, but also in other solar system bodies, is incredibly powerful. But also, to a greater or lesser extent, depending on the body, they provide for us a sense of temporal evolution, which is also important. So one of the things that I think Kathy mentioned that I think is really important to emphasize is that we're going to be looking at these targets in just a sort of snapshot of what could be a very complex evolutionary history. And I think it's, having an instinct for the extent to which some of these observational characteristics can change over time is both sort of important from the perspective of giving us some amount of humility, but is also useful because it allows us to probe sort of mechanistic models for what we think explain various signatures. So it gives you another thing to test, not just can you tune a model to give you this particular modern observation, but can your model also produce a particular temporal evolution? And so I think solar system objects in that respect are also really important. They give us a time dimension for testing sort of conceptual and theoretical constructs that I think is really uniquely powerful.
Yeah, those are wonderful answers. So given the given the difficulty of observing exoplanets, period, this search for life on exoplanets is going to be one step more challenging than just characterizing exoplanets themselves. So my question is, how do we do this without fooling ourselves? What makes a good biosignature, and how can we distinguish true biosignatures from false positives? And maybe this is a question that Eddie or Chris could start with, since I know you both work in this area and you're coming at it from different perspectives.
Yeah, so I mean, generally a biosignature is defined as a substance, object, or pattern that is produced by life and separable from other processes that could create abiotic processes. And so for one example that's common is metabolic output of gases. So there's oxygen in our atmosphere. Almost all of that's from photosynthesis by plants and cyanobacteria and algae. And another example would be methane from methanogenesis, which is a chemosynthetic metabolism of certain archaea. And so there's some requirements that those outputs have to have. I mean, they have to have absorption features that are detectable remotely, because we're always going to be viewing these remotely. They have to be survivable in the atmosphere, so they can't be immediately destroyed. And again, they have to be specific to biology. And so some examples in our atmosphere are oxygen, ozone, methane, nitrous oxide, and of course the spectrum of Earth's atmosphere shows the absorption features of all of those gases in conjunction with water vapor and carbon dioxide, which tell you or can give you indication it's a habitable planet. So those are compatible observations, and that context is critically important. And another thing you might look for is the disequilibrium of those gases. The fact that methane and oxygen nominally destroy each other, and so you need a constant output of one or both of those, at least abundant of those gases, in order to maintain that disequilibrium. That gives you, an idea of how much must be coming into the atmosphere at a given time. And so, I mean, that whole process is something that, to really fully understand, you need the geochemists and the biologists and the atmospheric chemists, and you need all those models in order to make that interpretation, and of course a stellar characterization. And so that's what a biosignature is. And then how could we be fooled? Well, we could be fooled in a couple ways, and this is the false positive that you allude to, is that we could see an absorption feature and misattribute that to a gas that's not producing. In other words, we could say something. We could have a gas where there are absorption features that overlap with each other, and so we could accidentally attribute this feature to a gas, and in fact, that gas is not present in the atmosphere; it's a different gas. And then we could potentially detect the right gas, but misinterpret the process that creates it. And so perhaps there is an abiotic planetary process that would make this oxygen, for example, and then we'd misattribute that to biology. And so really understanding, the full range of planetary processes that could produce what would otherwise be biosignatures is really important, endeavor in order not to be fooled.
Yeah, that's beautiful, Eddie. I have very little to add to that, except to maybe just reinforce the notion that a lot of the interesting work, I think, recently now and sort of into the future is centered on these potential false positives and also false negatives. So ways in which we might not detect a particular biosignature gas, even though it's being produced by a biosphere, because it's being destroyed by some other process sort of on the way. And there's a lot of really interesting work going on, sort of trying to spin up ways of making abiotic oxygen, for instance, and then trying to delineate ways that one might sort of diagnose these pathological high oxygen cases. So what are some other observations, other species of gas, particular abundance features, sort of context clues like atmospheric pressure, some of the other observations that we might be able to make to sort of rule these things out. So I think that's, in the coming years, there's going to be a lot of bandwidth and a lot of really fascinating stuff done, trying to sort of, measure twice and cut once to make sure that that we don't fool ourselves.
Yeah, it's certainly going to be a challenge, but I think we as a community are up to that challenge. I'm optimistic. So I understand there are a few audience questions. So in the last 10-ish minutes of this panel, I'd like to open the floor to audience questions.
Yeah, great. Thanks, Giada. So, you were just talking about false positives, the data, and I would assume I'll see a nod of heads when I say more data is better, right? That kind of thing. Yeah, there you go. So that being the case, we talked earlier in the conference about the data deluge. So you start getting all of this mass quantities of data. How do you work it, especially interdisciplinary, sharing it across all of these different groups, people involved, all the specialists. So what are you guys thinking now about that flood and how you're going to work with it? I don't know where to start with that one. Allison.
Okay. I would say, where we've seen the most data flooding is in heliophysics, where we're not counting photons, we're throwing them away, and we have more than we can possibly deal with on a daily basis flooding into our data centers. And we're really working on developing machine learning algorithms that can help with what we're seeing. And we could even limit the amount of data that we have to download then. And now I know, that scientists tend to say, oh gosh, don't throw away any data. But at some point, you're going to get so much that you can't possibly have a human look at it all. So yes, your machine learning algorithms are going to have to be pretty good. But we've seen success in heliophysics. And I think leveraging that work into astrophysics is another interdisciplinary area that can really help with the data deluge.
Anybody else?
Yeah, I'd like to emphasize the importance of funding and research and analysis support, because I've seen two cases so far: the Cassini mission, which I had the opportunity to work on, and then I worked on the Rosetta mission, which as soon as we arrived at the comet, and for 2 years, we got this fire hose of data, and we really just skimmed off the top with the publications that we managed to get out. But there's the Cassini Data Analysis Program that funds research using Cassini data, because there's so much more data than has actually turned into publications. And then the Rosetta Data Analysis Program also provided opportunities to dig more into the data. So I think it's going to be very important to support programs that fund people's time to work with this data. It takes time and it takes funding to do that. And that needs to be a big emphasis for the future once we start getting data in.
Okay, it's an interesting point about the funding. What about, and Allison talked earlier about having developed a tool that hasn't even launched yet, and how long some of this stuff takes. What's a better path going forward in your guys' opinions? Is it the big flagships that take a long time to develop and get up there and they're really valuable tools? Or might we be better off with, okay, well, let's get something smaller, more specific up there quicker and start getting a single line of data faster? Is there a better path, and how do we make those decisions?
Can we say both?
I was just about to say,
why not both?
Yeah, I was going to say a diverse portfolio, just like with investments. With science investments, you need a diverse portfolio of size of mission depending on the science return you're trying to get and the target that you're going to. And there's value in all scales of missions as long as there's proper science return that's matching that scale.
Well, and I think the person that would, if the why not both question, the people holding the funds have a pretty good answer for that. So again, it's prioritization and determining, okay, which one? What are we going to do? And yeah, I know the decadal points to that, but are there any other means by which we make those decisions? And what discoveries might influence those decisions significantly?
Well, I think we've seen this in earth science, where we've got now an administration that is finally really I don't want to get political, but it's really focused on science goals and increasing that funding and getting public awareness, because a lot of science development is coming from taxpayer money, and convincing the taxpayers that we've got a problem is one way to get more money. So you see that with weather and earth science. But yeah, I think with exoplanets, especially the developments that, and I'll put it out there for you guys, great science over the last 20 years has excited the public about the idea of exo-Earths. And we really aren't going to ever image an exo-Earth without a flagship scale mission. I think I believe that. I remain to be proven wrong, but I think it needs to be an ambitious mission. And I think that there's support out there for it. And, advocacy is all of our jobs in this field. So I think that's key to it as well.
Okay, sorry about that. So let's see. So, we talked, there was mention of generalists, and this is interdisciplinary. So let's go around the table. Who isn't currently at the table that should be? Who isn't involved right now that you think, should be when we're talking about unifying space sciences? Ready?
Well, I mean, I think there's a difference between people who are interested and people who are contributing to the maximum efficiency, right? And so that is in part the structures in which people are operating and the structures in which people are being funded. And so at the end of the day, a lot of scientists are spending some of the time trying to secure funding for the next few years, and they're not necessarily doing the science that they want to be doing. And so there's a duty cycle in this. And so facilitating more interdisciplinary work will help make this process more efficient. It'll help bring more people in to the process, and it'll make them more effective in that process. And I think the other thing that we should do is encourage people to be more generalists. In other words, I think that there is because of this funding issue, I mean, there is a kind of, there are a lot of incentives to be more and more of a specialist, or at least there has been historically. And so if that were lifted a bit, it would give people a little bit more freedom to embrace that more of a more generalist identity.
Anybody else?
I would say the one other group that I wish would get to the table more is the folks that maybe have outside funding beyond government funding. You're seeing a lot of interest in space in general with Jeff Bezos. I'd love to have him come to the table, or and get interested in really making a difference for long-term science as other interests. I mean, what's going to be here? We're not going to have 5G satellites and Starlinks in 100 years, but in 500 years, what's going to be memorable and what's going to be remembered from our generation? And maybe it is discovering the next exo-Earth, and maybe we can appease to that side of them to take an interest in the basic science.
So that's an interesting point. Aside from a couple of billionaires, and even them included, what's the incentive? What would be their reason to throw money at a project to look at exoplanets and see what's out there?
Ask them to ask their 5-year-olds, ask their kids, what drives their curiosity.
It's a great point.
I love that answer.
Yeah, that's very well put.
So, Allison, you mentioned this might be something of a pedestrian question, but you mentioned that with the loss of Hubble, we lose UV. Is that how critical is that? And if it is so critical, why is that being allowed to happen? If I got that right.
Yeah, and I think Kathy brought it up first.
Yeah.
I'm sorry, Kathy.
That was my point.
But yeah, and I'll let the science folks speak to it. But I've heard that resonated a lot, and that we need more UV, and I think that's another place where smaller missions can fill a gap. So go ahead, Kathy.
Yeah, I definitely agree that smaller missions can fill a gap until we have a strategic mission, something like LUVOIR or HabEx. But I can't say why that has happened. I know that people have proposed smaller missions, smaller telescopes that are in the UV that have not been selected. But I think that this is something that the community needs to really focus on, and that NASA needs to focus on, and really consider replacing that capability with the Hubble Space Telescope, because we aren't going to have Hubble forever. I would love to have Hubble forever, but at some point we're going to lose this capability, and we really need to be thinking ahead to what we're going to do, because the UV observations with Hubble have contributed to such a broad range of science discoveries that it needs to be replaced, that capability.
Very good.
I can add to that just briefly.
Real quick.
Yeah, these are the UV is the energies that are breaking apart the molecules in the planetary atmosphere. I mean, they're really important for characterizing the planetary atmospheres. So understanding the star. Got it.
Fantastic. Well, sorry, we're out of time. Giada, everybody, thank you so much. This is really cool. We really appreciate you being here, and thank you again.
Thank you so much to our panelists. I think this was a wonderful session. I hope you all learned as much as I did and had as good a time as I did moderating this.
Indeed. Thanks again. Okay, so now everybody can jump over to our next session to hear from our speaker, Goddard Plus speaker, Representative Don Beyer. Thanks, everybody.
Thanks, everyone.